Welcome, everybody. Good afternoon. And I want to welcome all the Insight participants, as well as all the online participants to this event, this course, which will be given by Professor Youssef Azouzi from Tunisia. And I'm particularly delighted to have this event at ICMAT and to have Youssef come for this period of 6 weeks. That's the length of the stay he's going to conduct here at ICMAT. I think this is a great opportunity to strengthen the relations between the Tunisian and the Spanish mathematical communities. I want to thank also Pedro Tradacete, the local researcher who's hosting Youssef here today. And I hope that this is a very useful event for everybody, for all the participants. I want to stress that ICMAT has a strong tradition of international cooperation, and that we collaborate with many mathematical communities from around the world, in Latin America, in Africa in this case, in Asia. And we are delighted to have this event here today, as I say. So with no further ado, I want to introduce Pedro, who will introduce our speaker. Thank you very much.
Okay, thank you, Javier. Thank you very much. So it is our pleasure to start this course today with Youssef Azouzi from the University of Carthage in Tunisia, who will be giving us an overview of nets in vector lattices and other aspects of functional analysis. So please.
Thank you very much, Pedro, and I thank SEMPA for giving me this opportunity to give this course. In fact, I want the course to be useful, especially for students that not introduced to nets. And I do not claim that it's very useful for expert people working on vector lattices and Banach lattices and topology. The course is about, the main topic of the course is about nets. I can say that there is 4 parts. The first part, I will speak about nets in topological space. Then this is more common topic than special nets. A special topic is about nets in vector lattices and Banach lattices. And in the section, I will speak about some types of convergence, especially order convergence. And unbounded order convergence. These convergences are studied in vector lattices. But we can speak about some type of convergence that is studied in Banach lattice when we need the order and the norm together, which is the unbounded norm convergence. This is is connected to convergence in measure. We can think of it like an abstraction of convergence in measure. And for unbounded order convergence, this is the abstraction of almost everywhere convergence. A very small part will focus on convergence structure. This theory of convergence structures and convergence space contains all things. So here there is some convergence that are not topological, like order convergence. And nets are very useful in this kind of situation. And last part, it's about, we focus on a special topic that I call diagonal principle, which is a generalization of the famous diagonal principle of Cantor, diagonal argument. This is the plan. Now I will start by giving the definition and basic results about nets, but this part is given in the context of topological space. So the motivation that in metric spaces, for example, continuity of functions can be expressed in terms of sequences. And this does not extend to general topological space. But there exists a broader notion that does work and enable proof to be carried out in a similar manner, in analogous manner to sequences. And such an approach often provides valuable insight and also intuition. I will start by giving the definition. What's a net? So a net is a map alpha defined from A to X when A is a directed set. I will say pre-ordered directed set, and X is a set. All sets will be non-empty to do some theory. So I should explain what does mean directed and pre-ordered. So pre-ordered set means a set equipped with a relation such that we have two conditions. This binary relation is reflexive. This means that X is less or equal than X for every X in A. And it is transitive. This means that if X is less or equal than Y and Y is less or equal than Z, then X is less or equal than Z. Here we miss the antisymmetric property to get an order. In general, often we deal with nets defined on ordered set, in fact. And directed means that if we take two elements in A, say alpha, beta, for every alpha, beta in A, there exists some gamma more or equal than alpha and more or equal than beta. Of course, this means that alpha is less or equal than. I will use the terminology of order to say more or equal, less or equal. Yes. Move it a bit down. Okay, to be seen.
So that everyone can see.
Yes. Okay. Right. So to give an example of nets, we should in fact give example of directed sets and maps. Nets are generalization of sequence. So a sequence is a net. Here M is equal to N. Sometimes we use this. This is a very common net that if we take X set and we take A equal to all finite subsets of X. Then we can define a net indexed by A. So every map alpha from A to another set, such that for F we write XF. F is a subset. This is a net. For example, I will take a function. If we take a set from A to Rx, for every F, I will take XF, the adjective function. Another example is the following, and it's an interesting example. If we work in topological space, if we take X topological space, and for every element X, we can take the set of neighborhood of X. So for every neighborhood of X, I can define an element in this neighborhood, any element. This gives us a net, xv and x by v. So the index set here is the set of neighborhoods. What is the relation here? If we want to study continuity, for example, then we are interested to be closer to X. So we take this order. We will say that V is less or equal than W if W is contained in reverse enclosure. We will see later that this net converges to X. I want to mention some trick as an example. If you consider two nets indexed by two sets, in general, sequences are indexed by n, so I can add two sequences because we have the same index. But if we take a different subset of index, A and B, and we want, for example, if we work in a vector space, so we are able to take the sum. So what we do here, we consider this net, this set, ordered by pointwise order. So in this set, we write that alpha beta is less or equal than alpha prime beta prime if alpha less or equal than alpha prime and beta less or equal than beta prime. And then we can define new nets indexed by alpha beta simply equal to X alpha. Here we ignore the beta, and Y beta, alpha beta, is equal to Y beta. And then really when we do the sum, we have exactly X alpha plus Y beta. This is useful when we want to study Cauchy nets, because the sequence is a Cauchy if the difference goes to 0 when both index go to infinity. And in this case, if we start with a net X alpha, we can consider this net X alpha minus X beta. So we assume here that we work in some vector space, and this is indexed by alpha beta. So this is a net used when we work with Cauchy nets. Okay. Now I will start by giving an example showing that sequences are not sufficient, and give after that some results using nets that generalize results known for sequences in metric space. In this example, we take X uncountable set. So let X be an uncountable set. We will define a topology on X. So we define a topology O in X as follows. So V belongs to 2 if only if V is empty or the complement of V is countable. So we can check that this is a topology, and we can prove that in X, if we take a sequence xn in X is convergent if only if it is stationary. This means that there exists some n0 such that xn equal to xn0 for all n more or equal than n0. Second property of this space that we can find some element that belongs to the closure of a set. The second property, if we take an element A belongs to X and S is X minus A, then the closure of S is X, because the closure is S or X, but the set A is not empty. But we cannot find, there is no sequence in S that converges to A. So also, if we take any map from X to another set Y, I will say R, for example, then this map is sequentially continuous, because if we take a sequence that converges to an element, then it is stationary. However, so I can say that then F is sequentially continuous, because we use the first property. But for example, if you take the identity map from X to R, if we take x equal to I. So this topology can be defined in any uncountable set, in particular for R. And here we take the usual topology. This map is not continuous. This is not continuous. For example, because the image of the pre-image of an open interval is not open. So these simple examples can show that sequences cannot be used to characterize any property studied in general topological space. Also, we will see some example about compactness. That we'll give an example of compact space such that there is a sequence having no convergent subsequence. Now I will give some property that can be characterized via nets. First result, I recall that a topological space is Hausdorff if we take two different elements, then we can find two disjoint neighborhoods, disjoint open sets, each of them containing one of the points. And we have this equivalent for a topological space the following are equivalent. I will call it X. X is Hausdorff. And every net has at most one limit. So the property to being Hausdorff is simply equivalent to the fact that limit is unique. I will prove this property. And proofs here are given to be familiar with nets. I want that nets would be a very natural tool to use. I claim that most of the proofs are natural. So we assume that the space is Hausdorff, and we will show that every net has at most one limit. Maybe before giving the proof, I want to introduce two terminologies. Some terminology. I will say that the net X alpha is frequently in a set S if for every, I will index by A, for every alpha in A, there exists beta more or equal than alpha, such that X alpha belongs to S. This is a very related to string cluster point beta. X beta, X beta. Thank you. Second, so the net X alpha is eventually in S if there exists alpha 0 such that x alpha belongs to S for all alpha more or equal than alpha 0. This is mostly used to characterize cluster points, limit point, and this is used for convergence. Of course, we need to define convergence. I give the statement here without introducing the notion of convergence. It's very natural. Definition. Let X be a topological space. We say that the net X alpha converges to X if for every V neighborhood of X, X alpha is eventually in V. This means that there exists some alpha 0 such that can make an observation. All of these are before giving the proof. If we come back here, and if we take a net that is frequently in S and frequently in T, if X alpha is frequently in both S and T, then X alpha is frequently in S in union T. And if X alpha is eventually in S and T, then X alpha is eventually in S the intersection. Now I come back to the proof of the proposition. I want to show that if the space is Hausdorff, then limits are unique. They assume that the space is Hausdorff, and I take a net. And I will argue by contradiction and assume that the net has two limits. So assume that X alpha converges to X and X alpha converges to Y. And I want to show that X is equal to Y. And I will argue by contradiction and assume also that with X different of Y, then as X alpha converges to X, the net is eventually in any fixed neighborhood So we will take, let V belongs to Nx, neighborhood of X, W a neighborhood of Y, and as the space is outdoor of, I can assume that the intersection is empty. But if I use this observation, the net is eventually in V and eventually in W, and then it is eventually in the intersection. So there is an element of the net which belongs to the intersection, which gives a contradiction. So we get a contradiction using observation 2. Just for observation 2, it's I can quickly say why we have this, because there exists some alpha 1 such that, just to use the fact that the set is directed. So I will try it here. So there is some alpha 1 such that X alpha belongs to S if alpha more or equal than alpha 1, and there is alpha 2 such that X alpha belongs to T for alpha more or equal than alpha 2. Now, as the set is directed, I can choose some beta more or equal than alpha 1 and more or equal than beta 2, and I get for alpha 0 more or equal than alpha 1 and alpha 2 at the same time, we have alpha more or equal than alpha 0 implies alpha X alpha is in S and X alpha is in T. Okay, so the assumption to be directed is done for this type of argument. Now we give a statement for continuity using nets. It's a very natural statement, so I can say that it's a theorem. Let F be a map from a topological space X to a topological space Y, and Y are topological space. And the following are equivalent. F is continuous at x0. An expected property that if x alpha converges to x0 in X, then f of x alpha converges to f of x0 in Y. Okay. For the proof, even if we don't see the statement, it's okay. So I will prove that 1 implies 2. I will assume the continuity, and I take x alpha in X such that x alpha converges to X. In a natural way, to show that f of x alpha converges to f of x0, I will take a neighborhood of x0, of f of x0, and I want to show that after some time the net f of x alpha. So I have to prove that there exists some alpha 0 such that f of x alpha belongs to W for alpha more or equal than alpha 0. Or this means that or equivalently, X alpha belongs to F minus 1 of W or more or equal for alpha. But as F is continuous, we know that this is a neighborhood of X. So as F is continuous at x0, F minus 1 of W is a neighborhood of x0. And now, as X alpha converges to x0, alpha 0 exists. Proofs are in general very similar to proofs used for done for sequences, but we need to take some care. Some properties are not working in general. I will give some examples that work for sequences, but does not work for nets. But I will start by giving positive result. Now I assume that this property is satisfied, and I want to show that F is continuous at x0. F is continuous at x0 means that if we take a neighborhood of F of x0, I want to show that F minus 1 of W is a neighborhood of x0. This is what I need to show. If not, for every neighborhood of x0, there is some point in this neighborhood that does not belong to, there is some point here. Otherwise, for every V neighborhood of x0, V is not contained here. So V is not contained. So there exists xV belongs to V minus F minus 1 of W. Now I recall that I gave an example of net and said that it is very important. And it's very important. Now we want to show that xv converge to x0, but f of xv does not belong to 1. And this shows that f of xv does not converge to f of x0. The only thing that I didn't show was this one. This one is a general fact, so I give the proof of this. This is a general fact. If you take a neighborhood of x0 and you choose any element of this neighborhood called xv, then xv converges to x0. What does it mean that xv converges to x0? So the net xv is indexed And I want to show that this net converges to x0. This means that if I take a neighborhood of x0, I can find some v0 such that this plays the role of alpha. Okay, so let w, I take n, a neighborhood of x0, and I want to show some v0 such that if v more or equal than v0, then xv belongs to n. But what does mean that v is more or equal than v0? This means that v0 is contained, v is contained in v0. And it is sufficient to choose n equal, choose v0 equal to n. Because if we choose v0 equal to n, we have v contained in n, then xv belongs to v by definition, and v is contained in n. So this work. This is a very important and simple example of converging. This replaces in some sense the fact that if you take an element in the ball, then this sequence converges to x0. Okay, now we were able to give a property equivalent to Bing-Hausdorff and continuity. Now another result. Again, we take X a topological space, and I take S the subset of X and A element of X. Now we give a characterization of being in the closure. So A belongs to the closure of S if and only if there exists a net in S that converges to A. So S is closed if and only if for every net in S that converges to A, we have A in X. So S is closed under taking limits. And also characterize open sets. S is open if and only if for every converging net x alpha to an element A in S, we have x alpha is eventually in S. I will give the proof. These properties are very similar to what happened in matrix space or sequences. Okay, assume that A is in the closure. Then by definition, for every V a neighborhood of A, the intersection with S is non-empty. So it exists X V in V and in S. And you observe that the net XV is in S. And using this fact, XV converges to A. For the converse, so assume that X alpha converges to A and X alpha belongs to S for every alpha. Then if we take any neighborhood, it's pretty easy. If you take a neighborhood of A, then the net is eventually in this neighborhood. So it exists alpha 0 such that alpha more or equal than alpha 0 implies X alpha belongs to V, but then X alpha 0 belongs to V and S. So the intersection is not empty. The second property follows from the first, and this is very similar. So I will skip, can be an exercise. Now I will speak about topology or coarser topology. If we take a set X and we take a family of map from X to yi, where yi is a topological space. But here X is a set. We can define the coarser topology, making all these functions continuous. Left O, the coarser topology, making is function continuous. We know that this topology no value of this topology. So if Vi is an open set in Yi, then for this topology, Fi minus 1 of Vi should be open. And if we take finite intersection, also, now if I here belongs to some set like I, then if we take this is open, if A is fine. And if we consider the topology consisting of all union of these subsets, we get 2. So 2 is, this is a base of topology for 2. Now I want to explore nets. So we have this result. X alpha converge to X in this topology if only if Fi of X alpha converge to Fi of X for every I. As a special case, but important case, if we take X, the product of Yi, we get the product topology. This topology is a closest making projection Ei from X, Yi to Xj. We take the component X. This is our Fi. And for this topology, we know what is convergence of nets. So I will prove this proposition. And then I will use it to give a proof of Tikhonov theorem with nets that the product, any product of compact spaces is compact. At the end of the course, I will give a short proof of Tikhonov theorem using diagonal process. The proof. So assume that X alpha converge to X. This is trivial. And as Fi is continuous, already done this, we have Fi of X alpha converge to Fi of X. For the converse, now assume that Fi of X alpha converge to fi of x for every I. And we want to show that x alpha converges to x. So we take a neighborhood of x. Let V be a neighborhood of x. As this is a base of topology, then this neighborhood contains something like that. So there exists a finite set in I such that, and open and Vi in Yi such that the intersection of it's not good to take to index by A. I will take this F final set. Usually I take a net indexed by a set A. So this is contained in V. Okay, can choose this open, and we assume that, okay, observe here that as x is here, so fi of x is in the I. Now, as fi of x alpha converges to fi of x, then we can find alpha I such that for alpha more or equal than alpha I, we have fi of x alpha belongs to Vi. And then this means that x alpha belongs to fi minus 1 Vi. Or if we use the terminology introduced above, this means that x alpha is eventually in fi minus 1 Vi. And then if you take a finite intersection, then it's okay. So this happens for finite many times. So x alpha, this is for every I in F. And as F is finite, we can take the intersection. So x alpha is eventually in the intersection, which contained in our neighborhood V. Okay.
Let's make a break now.
Oh,
It's 4 o'clock.
okay.
Want to make a break now?
Well, okay, make a break.
So we'll do a 10 minutes break and reconvene at 4:10.
Any question? So, come back. Just I will make some remark. Maybe it should be made before, but nets, it's to say that nets characterize topology. So if we know convergent nets, we know the topology. This is not not the case for sequences. For example, if we look at the first example I gave, convergence sequences are stationary sequences. It's the same if we take the topology given by X and empty, the smallest topology. But for this topology, no, the discrete topology. For the discrete topology, all the stationary sequences converge. And then we have two different topology, but we have the same convergence sequences, which is the same if we take the space L1 and we use Schur theorem. So for L1, the weak topology is different from the norm topology. I recall that the weak topology is a topology given by continuous function. So you take X, a normed space, and X star its dual. So X star given functions, all functions from X to R, for example, to work with R. And if you take these maps and we use the coarser topology, so we get the weak topology. And for infinite dimensional space, weak topology is different from norm topology. But we have Schur theorem that for L1, then a sequence converge to in norm or weakly, it's the same thing. So we have the same convergence sequences, but topologies are different. Okay, now I speak about compactness. And I want to prove a theorem similar to what done for metric case. For a metric space is compact if only if every sequence has a convergent subsequence. So we need to introduce the notion of, similar to the analogous notion to subsequence, which called subnet. And then we prove the following. I will give a statement, although the notion of subnets is not already introduced. So, and then this result will be used to give another proof of Tikhonov theorem. Let X be the topological space. The following are equivalent. X is compact. Every net in X has a conversion subnet. But before, I need to give the definition of subnet. A subsequence is a sequence indexed by the same set, by A. And just we take a subset of terms in increasing way. And sometimes when we prove something using subsequence and we construct subsequence, sometimes we need to make a care about the map phi. For subsequence, we need a map phi from n that is strictly increasing. I will make a remark of later that maybe the theory of subsequence could be developed without assuming that this condition. It makes many proofs easier. We need just some map such that phi of n converges to infinity when n goes to infinity, something like that. So this condition of being increasing is not used for subnet. So first I define what's cofinal map. So if we take two-directed cofinal map, I will say a map phi from A to B. I will take let A and B be two directed sets. Then a map from A to B is usually we consider a net indexed by A and we take a subnet indexed by B. For this reason, I will take from B to A is cofinal. If for every alpha in A here, there exists, I will say for every alpha 0 in A, there exists some beta 0 in B such that phi of beta is more or equal than alpha 0 whenever beta is more or equal than beta 0. For if we work with n, so we need just the condition I already put here, that we need just that phi of n converges to tends to infinity. This means that if we consider phi beta for beta more or equal than alpha 0, this state, then it is contained in alpha. Okay. Now a subnet, let X alpha belongs to A, B, net in some space X. The subnet of X alpha is a net Y beta such that Y beta is equal to X phi of beta for some phi from B to A cofinal. So to have a subnet, we need to have a cofinal map, and our subnet is indexed by a new set. This is a very special, so and different from sequences. To define a subnet, we can work with a set which can be bigger than the initial set. Okay. It is easy to see that if a net converges to X, then each subnet also converges to X. So if X alpha converges to X and Y beta is a subnet of X alpha, then Y beta converge also to X. But we can have a net that does not converge. And this net can have some subnets that converge. And a limit of a subnet is called a cluster point. Cluster point, I will abbreviate it in CP, of X alpha is a limit of some converging subnet of X. Okay. Now we come back to our theorem about compactness. We will prove that compactness can be characterized by this property. So, proof. One applies to, I assume that the space is compact, and I take a net in X. I want to show that this net has a converging subnet. Or I want to show that there is some X which is a cluster point. Now assume that X alpha has no cluster point. So I will show that X is not compact. I can find, okay. Then for X in X, X is not a cluster point. So there exists an open set Vx, which is a neighborhood of X, such that X alpha is not frequently in Vx. I will show later that this is maybe be obvious, but I will prove it. I will use later that X is a cluster point if only if X alpha is frequently in any neighborhood of X. I will use this fact and then prove it. So if X is not a cluster point, then we can find a neighborhood of X such that X alpha is not frequently in this neighborhood. This means that there exists alpha X such that X alpha does not belong to Vx for all alpha more or equal than alpha X. This means that the net is not frequently in the neighborhood. Now, if X run over X, big X, then we have this cover from the open cover X. We extract a finite cover, say X with F is finite. Now, observe that for every X here, there is an alpha X such that X alpha does not in Vx. So as F is finite, we can find alpha 0 in A such that alpha 0 more or equal than alpha X for every X in F. Here we use the fact that set is directed. This is done for 2 or for finite elements. It's the same. So for every alpha more or equal than alpha 0, X alpha does not belong to every Vx. So alpha X does not belong to X, because X is the union of these contradictions. Nice. Okay, this proves that X, every net has a convergent subnet. Now 2 implies 1. We assume that every net has a convergent subnet, and we want to show that X is compact. So we start by taking an open cover of X. Most of the proofs are done by contradiction. So we assume by contradiction that there is no finite. So we argue by contradiction. And assume that for every F contained in I is F finite, the union does not give X. So we can find an element XF This is a very natural proof here. Assume that it's not compact, so for every finite set, the union does not cover X, and then there exists, I say that for every F, there exists XF belong to X minus the union. Here we have a net by assumption the net xf. You see this net, so it's indexed by all finite set. I will say gamma. Gamma is the as a cluster point x. Here gamma is the collection of finite subsets of x ordered by inclusion. Right. So x now is the cluster point of this one. So x belongs to some vi. So there exists I0 such that x belongs to vi0. And the net has a cluster point x. So by the remark above, the net is frequently in any neighborhood of x. So it is frequently in this neighborhood. Then, so as x is cluster point of x alpha, if we take any element in the set, we will take the set consisting of this element. So for f0 equal to I0, we know that there exists f more or equal than f0. Observe that here the order is the inclusion. So E0 belongs to f such that x with this index belongs to the I0. But as I0 is in F, this is contained in the union. But by definition, XF is not here. This contradicts the definition of XF. XF is taken outside this set. So here it's very natural proof. Okay. If compactness, you want to give as an application of this a proof. This proof is, I think, published in the American Monthly Journal in the 19th. A proof of Tikhonov theorem using nets. Mucho? Yes, we need mucho. Tikhonov theorem with nets. I want to introduce some terminology before giving the statement of the theorem and the proof. For Tikhonov theorem, we take X as a product of topological space. And we assume that every xi is compact. And want to show that X is compact. Now, if we fix net x alpha in X, and for the ith projection, we will write x alpha x is x alpha equal to x alpha of r. And we will say that A belongs if we take a subset of I and we take A here, we will say that A is a partial cluster point. I will abbreviate in ECP of x alpha if x alpha of I converge to A of I for every I in J. I recall that x alpha is convergent to X if only if. Here we recall that x alpha converges to X if only if x alpha of I converge to X of I for every I in I. Okay. And if, of course, if J is equal to I itself, then it's a cluster point. Here for some better for some subnet. It's not a limit, it's a cluster point. Okay. The theorem, I recall the theorem very now. If xi is compact for each I, then X, the product of all these spaces, is also compact. For the proof, I will use Zorn's lemma by defining some ordered set and maximal element. So let x alpha be a net in X. We consider this set consider the set F equals to all where J X, I will say Yj, where J is contained in I and Yj is a partial cluster point of Yj belongs to this product is a partial cluster point of X alpha. Okay. First observe that the set F is not empty because so first F is not empty we can just take any element I and you take yi is the cluster point of x alpha of I. This is a net in xi, which is compact, so it has a cluster point. Now, f is ordered by in a very natural order, j y j less or equal than k y k. If j is contained in k and yk can be seen as yk if you take the restriction on j is equal to yj. What time is it? 20 minutes. 20 minutes. Okay. So we can show that every chain in F has an upper bound. Just we take, so then check easily that every chain in F has an upper bound. And then by Zorn's lemma, there exists a maximal element j x y j, and it is sufficient to show that j is equal to I. If j is different from I, if not, there exists I0 in I minus j. We have a subnet x beta. There exists a subnet x beta such that x beta of I converge to yj of I for every I in J. This is by definition, because this is a partial cluster point. Now, if we take the net I forgot to say, but it is very easy to see that the subnet of subnet is itself a subnet of the initial one. So if we take the subnet, what it's called here, x beta, I will say x1 beta. If I take the net x1 beta of I0, this is a subnet. This is a subnet in xi0, which is compact. So, as a convergent subnet that I called x2 gamma of I0. No, gamma is contained in some C, some gamma. Now, if we take K equal to J union R0, and you take X YK of I equal to Yj of I if I is in J, and as a convergence subnet to some Y of to some YE0, I say, or anything, A and 0. So just we extend the xk, we have the value, the limit on I0, then k x k y k is a partial cluster point, and it is bigger than the maximal element, which is a contradiction. This contradicts the maximality of our element. Okay, so we get that the set J is I and our point is the cluster point of the whole net. Okay. Just I give some strange definition of something called just some word, and then I give some exercise to see if things are clear or not, and then I will give some applications of nets. For the application, I will select some properties that always proved without nets. And I think that the proof with nets is easier. Sometimes is more difficult. At first, I want to mention some thing called universal net. What's a universal net? We take X alpha is universal. So X alpha is a net in X. X is a set. I will say that X alpha is universal if for every subset S in X, we have, after some time, the net is in S, or after some time, the net is not in S. So X alpha is eventually in S, or eventually in X minus S. And this happens for every set. I give two results about every net has the universal subnet. So the definition seems to be very strange. So, but we can show that. Also, the proof of this result use the Zorn's lemma. So there is some tricky proof. So every net has the universal subnet. And then we have a theorem. X is compact if only if every subnet is convergent. Okay. This proof of now you can use universal subnet to give a very short proof of Tikhonov theorem, but the difficulty is hidden here because for here this result has a long proof. There is a lot of proofs for Tikhonov theorem. The best I liked will be given in the last part of the course. Just some exercises. Not difficult here. I can say that these exercises are not difficult at all. Connected to sequences. If we have a sequence, if xn converge to x in a metric space or in a topological space, anyway, in x, then if you take all the sequence, the whole sequence, and you add the limit, this is compact. The question, is it true for nets? If you take a net that converges to x, you take the net and you add x. Does this give a compact set? Second exercise, if you take xn, if xn is a sequence in a metric space without cluster pool, then the set xn is a closed set. So is it true for nets? These two questions are not difficult. Another exercise. I will take Y compact. Assume that we deal with topological space. Assume that Y is compact and X is just a topological space. Then we consider the projection show that the projection P1 is closed. This means that the image of any closed set is a closed set. Now, the last question comes similar to graph theorem. We know that if we have linear functions between two Banach spaces, then a linear operator between two Banach spaces, then T is continuous if only if the graph is closed. Now we take f from x to y, and we assume that y is compact and Hausdorff. If the graph of f is closed in x cross y, then f is continuous. The statement is true. Okay. Done. Okay. Next time I will give some applications, some proofs using net.